Imagine a world where your phone downloads movies in the blink of an eye. Picture self-driving cars communicating flawlessly. This is the promise of 5G. 5G is not just a faster 4G. It's a revolution in mobile technology, but this revolution needs a traffic controller. 5G handles many different types of data. Some data is urgent, some data is less time-sensitive. This is where quality of service QoS comes in. QoS is like a priority system for data. It ensures that important data gets through even when the network is busy. Without QoS, 5G would be chaotic. Imagine a surgeon performing remote surgery. The video feed needs to be perfect. Any lag could be disastrous. QoS guarantees this smooth connection. Or think about self-driving cars. They need instant information to avoid accidents. QoS makes this possible. QoS is the unsung hero of 5G. It may be invisible to the user, but its impact is felt in every facet of our connected lives. In the vast network of 5G, data travels through different paths. One crucial path is the user plane. This is where your data takes center stage. But how do we ensure that this data reaches its destination with the right priority? This is where SDAP steps in. SDAP stands for Service Data Adaptation Protocol. It's like a conductor of an orchestra. It makes sure every instrument plays its part perfectly. SDAP manages the QoS of your data in the user plane. It's the reason why your video call doesn't drop when you open a web page. Think of SDAP as a sophisticated traffic management system. It analyzes data packets, it assigns them to different queues based on their priority. This ensures that time-sensitive data, like voice calls, gets VIP treatment. SDAP is essential for a seamless 5G experience. It's the invisible hand that guarantees the quality of your data. Without SDAP, the promise of 5G would be a distant dream. 5G is built on a complex architecture. Think of it as a layered cake. Each layer has a special function. This layered structure is called the protocol stack. SDAP has a specific place in this stack. It resides in the user plane. The user plane is responsible for transmitting your data. SDAP operates just above the PDCP, Packet Data Convergence Protocol layer. It receives data packets from PDCP, then it adds its own QoS information. This information tells the network how to handle the data. SDAP doesn't work alone. It interacts with other layers in the stack. For example, it works with the Radio Resource Control (RRC) layer. The RRC layer helps set up the initial QoS rules. SDAP then enforces these rules. Understanding SDAP's place in the protocol stack is crucial. It helps us appreciate how 5G delivers a seamless and efficient data experience. 5G didn't magically appear. It evolved from its predecessor LTE, long-term evolution. LTE also had QoS mechanisms, but SDAP in 5G is more advanced. Let's compare them to understand why. LTE used a protocol called PDCP for QoS. PDCP was good, but SDAP is better. SDAP is more flexible. It can handle different types of traffic more efficiently. This is crucial for the diverse demands of 5G. For example, imagine a factory using 5G to connect robots. These robots need ultra-reliable, low-latency communication. SDAP's flexibility allows it to prioritize this critical data. This wouldn't be possible with LTE's PDCP. SDAP is a testament to the evolution of mobile technology. It builds upon the strengths of LTE. It adds the advanced capabilities needed for the 5G era. Section 5. Unpacking the SDAP Toolkit, QoS Flow Mapping and QFI Marking. SDAP achieves its magic using several tools. Two of the most important are QoS Flow Mapping and QoS Flow ID, or QFI marking. These tools help SDAP prioritize data. QoS flow mapping is like sorting mail. SDAP looks at each data packet. It figures out what type of data it is. Is it a voice call? Is it a video stream? SDAP then assigns the packet to a specific QoS flow. Each QoS flow has different priorities. This ensures that the network handles the data correctly. For example, voice calls need low latency, so they are assigned to a high priority flow. Once the data is mapped to a flow, SDAP uses QFI marking. QFI stands for QoS Flow IDs. SDAP adds a special tag to each packet. This tag is like a VIP pass. It tells the network which flow the packet belongs to. QFI marking ensures that the data stays in its designated lane. It prevents lower priority data from clogging up the network. This is crucial for maintaining the quality of service. Section 6. SDAP's adaptive prowess, reflective QoS, and data adaptation. SDAP is not a static protocol, it's dynamic and responsive. It adapts to changing network conditions. This adaptability is made possible by two key functions: reflective QoS and data adaptation. Reflective QoS is like a feedback loop. SDAP constantly monitors the network. It receives feedback from other network elements. If the network is congested, SDAP knows. It can then adjust the QoS parameters. For example, SDAP can temporarily lower the priority of less important data. This ensures that critical data still gets through. Once the congestion eases, SDAP restores the original priorities. Data adaptation is another powerful tool in SDAP's arsenal. Sometimes the data itself needs to be adjusted. For example, a video stream can be compressed. This reduces its bandwidth requirements without sacrificing too much quality. SDAP can initiate this data adaptation. It acts as a mediator between the application and the network. This ensures optimal data delivery even in challenging network conditions. Section 7. SDAP in action. Prioritizing traffic for a seamless 5G experience. Let's see SDAP in action. Imagine you're in a crowded stadium. Thousands of people are using their phones. The 5G network is under heavy load. Without SDAP, chaos would ensue, but with SDAP, the network remains stable. SDAP prioritizes traffic. A surgeon in the stadium is performing a remote surgery. This application requires ultra-reliable, low-latency communication. SDAP ensures that this data gets top priority. The surgery continues uninterrupted. Meanwhile, you are streaming a live concert on your phone. This application is less critical. SDAP assigns it a lower priority. You might experience some buffering, but the video continues to play. At the same time, someone is uploading a large file. This application is not time-sensitive. SDAP gives it the lowest priority. The upload might take longer, but it will eventually complete. SDAP ensures that everyone gets the best possible experience, even when the network is under stress. Section 8. SDAP, a catalyst for 5G use cases, URLLC, eMBB, and mMTC. 5G is more than just fast downloads. It promises to revolutionize various industries. These diverse applications are grouped into three main use cases: URLLC, eMBB, and mMTC. URLLC stands for ultra-reliable, low-latency communications. This use case demands the highest level of reliability and the lowest possible latency. Think of remote surgery, factory automation, or self-driving cars. eMBB stands for Enhanced Mobile Broadband. This use case is all about speed and capacity. Imagine streaming 8K video, downloading huge files in seconds, or experiencing immersive virtual reality. mMTC stands for Massive Machine-Type Communications. This use case involves connecting millions of devices in a small area. Think smart cities, industrial IoT, or environmental monitoring. SDAP is crucial for enabling all three of these use cases. It allows the network to tailor its QoS parameters to the specific needs of each application. Without SDAP, the full potential of 5G would remain unrealized. Section 9. SDAP's evolving role, 5G SA versus NSA, and the road to 6G 5G is still evolving. Today we have two main deployment modes, 5G standalone SA and 5G non-standalone NSA. SDAP's role differs slightly in each mode. In 5G NSA, SDAP relies on the existing LTE core network. In 5G SA, SDAP is fully integrated into the new 5G core. This gives it more control and flexibility. As 5G matures, we can expect SDAP to become even more intelligent. It will leverage artificial intelligence and machine learning to optimize QoS dynamically. This will further enhance the 5G experience. Looking even further ahead, 6G is on the horizon. SDAP will play a crucial role in shaping the future of mobile communication. It will need to adapt to handle even higher speeds, lower latencies, and a greater diversity of devices and applications. SDAP is a testament to the ingenuity of engineers. It's a powerful tool that enables us to unlock the full potential of 5G and beyond.